Hi dear students, welcome to Wallah. This is Satish Kumar Durshetty, Faculty of Measurements and Instrumentation. Welcome to lecture number 3 of one shot series on this Wallah English channel. After the successful completion of 2 lectures, first lecture on bridges, second lecture on error analysis, here we are moving to the lecture number 3, which is measuring instruments. Measuring instruments is one of the important topic with respect to GATE examination, and not only GATE, other exams also. Because in measurements, to measure certain current, voltage, power, energy, we are having a set of instruments. So we are having n number of instruments, and each and every instrument is having different working formula and constructional features. Regularly we are getting some questions on this measuring instrument. Without wasting the time, let us go for today's class, and this is my agenda for today's class. We are going to discuss types of instruments, PMMC. What are the types of instruments? We are having a list of instruments. Under that, we'll try to cover in this lecture 2 instruments. One is the PMMC, other one is moving iron. PMMC, it's a torque and its formula expression, and a range extension for the PMMC. Next comes the moving iron, it's a torque and its formula, torque expression, how it works, and moving iron range extension. Okay, so without wasting the time, we'll go for the content. First, types of instruments. Basically, broadly speaking, instruments can be classified as, indicating instruments, okay, recording instruments, and integrating instruments. That is the basic classification. Indicating instruments, recording instruments, and integrating instruments. In indicating instruments, we are going to have only the present value indication, which are having the damper mechanism, which are having the pointer mechanism. Whereas in the recording instruments, the graph, the present value is going to be recorded. The best example is CRO. Whereas integrating instruments, the value is going to be accumulated over the period of time. Not only the present and upcoming data also going to be accumulated over the period of time. So in today's lecture, first we will cover the indicating instruments mostly. Of course, energy meter comes under integrating instrument. Remaining most of all the instruments are coming under indicating instrument. So here, the first one is the PMMC. The PMMC full form is permanent magnet moving coil. And its application is, it is only suitable for the DC. It is only suitable for the DC. Next comes the moving iron, and the moving iron is suitable for both DC and AC. Suitable for both DC and AC. Next comes the electrodynamometer. Electrodynamometer is also suitable for DC and AC. Hot wire, it is suitable for DC and AC. Electrostatic, actually electrostatic is majorly suitable for AC. High voltage. Rectifier type instruments are suitable for both DC and AC. Hall effector suitable for both DC and AC. Induction type are suitable for DC. Okay, so today's lecture, first we'll start with the PMMC. PMMC stands for permanent magnet moving coil, my dear. In permanent magnet moving coil, here in permanent magnet moving coil, 2 things you have to understand. Major features of the PMMC is, in PMMC we are having 2 things. One is the permanent magnet, the second is the moving coil. One is the permanent magnet, other one is the moving coil. So there is one permanent magnet which is going to generate the magnetic flux, and other one is a moving coil, which is the reason for the deflection. So if you see the constructional features, actually I want to draw this diagram. Okay, so we are having a permanent magnet. So this is our this is a permanent magnet, north pole and a south pole. Okay, so which is the reason for the magnetic flux density. And in the center we are having a spindle. So this is a spindle. So this is a spindle, and the spindle is placed with the ball bearings So there is a spindle here, patafat. In the spindle, on the spindle, we are going to have one coil. So this is the coil. And there is a group of coils, actually, group of turns, number of turns of the copper coil. And this is with a aluminum frame. Aluminum frame, and it is covered with an iron cylinder, covered with iron to radiate the flux, covered with a iron cylinder to radiate the flux. Okay, and here we are having this particular copper winding is connected to the spring So this is a spring connection here. Okay, so through this spring the current is going to enter and it travels into the copper winding, and then these are the two springs, and this is the magnetic flux released by the permanent magnet. So this magnetic flux density we are taking as B and the current as I, and this particular copper winding is having the number of turns N and the area of cross section of the copper winding is A. So here I want to talk about certain materials here. First of all, the permanent magnet. You see the permanent magnet is made by the material alnico. Materials are also important. Sometimes one mark questions are match the following expected. Next comes the coil, moving coil. The moving coil is mainly made by copper winding, copper. Okay na? and the springs which are connected to the spindle, the springs are having certain characteristic. The characteristic is they should allow the current. Okay, so they should allow the current, that's why they are conductive. So that should be conductive. The springs must be conductive. The springs must be conductive in nature and non-magnetic. They should not produce any magnetic field. Conductive in nature and non-magnetic. So that is a property of the spring material. So that is satisfied by phosphorus bronze. That is satisfied by phosphorus bronze. Phosphorus. Fundamentally, these are the materials that, and we are having a base. This particular, what do you say? This copper winding. The copper winding is having a frame, former. So that is what we call as former. So on which the copper winding is rotated. So that is made by aluminium. What it is made by? It is made by aluminium because it's having lightweight. And the cylinder. And the cylinder that is made by iron, that is ferrous iron, because iron is more permeable in nature. So because of the more permeability of the iron, the more amount of flux can be radiated in that particular around the copper winding. So these are certain materials. Okay, so please remember, between the two permanent one permanent magnet setup, north pole south pole setup, there is a copper winding. So now when the current is entering under a magnetic field, then what happens? That particular copper plate gets deflected. So because of the deflection, this particular setup experiences a deflection torque. Okay, so directly I am going to the formulas. The deflection torque experienced by the PMMC setup, the deflection torque experienced is given by formula BIN. BIN. Okay, so this is the formula that you have to remember. I am not going to the derivation part. So the deflection torque given by the PMMC is given by the formula BINA. So where B is called the magnetic flux density. B is called the magnetic flux density. The units are given as Weber per meter square or Tesla. Okay, and the I is the current passing. So this is only we have to measure current. Especially we are using the DC current. PMMC is best suitable for DC, not for AC, because if you give the AC current, the frequency of the AC current is 50 Hz. So for every second there is a 50 oscillations. So the current is changing its direction positive to negative. So that much faster rate the pointer cannot deflect, that much faster rate that the deflection cannot happen. It is a moving coil is not in a position to detect that much fastest rate. That's why that pointer will be stable. By oscillating at a maximum frequency, it cannot move, it cannot detect that oscillation. That is the reason only suitable for DC supply. So current, DC current, N is the number of turns. What is N? N is the number of turns of the copper winding, number of turns of copper winding. And A is the area of cross section, area of cross section of the copper. So that can be given as length into breadth. So where TD is called the deflection torque. So you must remember this formula, because in the exam we are going to get questions respect to this. So this particular TD is called deflection torque. What we call this as? Call this as deflection. Okay. So as per this diagram, because of the interaction of the current and the magnetic flux direction is like this. Okay, na? Magnetic flux direction is going like this and current direction is like this. Then what happens? It experiences a force. Because of the force, that copper winding is going to have a deflection. So this deflection is creating certain torque. So that torque is called deflection torque. But at the same time, these two springs are there na, which are connected to the electronic circuit. So these are going to our circuit. These are going to our instrument circuit. Okay. So now what happens? These particular springs which are having connectivity to the copper winding, whenever these plates are deflecting, so the springs are going to create a controlling torque. Okay, the springs are used to generate the controlling torque, and the controlling torque is given by the expression Tc is equal to Kc into theta. So please try to remember, controlling torque mostly same for all types of instruments, mostly. Tc is equal to Kc into theta, where K is called the spring constant. What we call this as Kc as spring constant. Okay, so Kc is a spring constant. Deflection torque units Newton meter. Okay, so Kc is the spring constant. Theta is the deflection. What is theta? Theta is called deflection. Okay, so these are the expression for the deflection torque and the controlling torque. So now what is a steady state? It's steady state. What happened now? There is a pointer here. So I am going to connect the pointer. So this particular pointer. Okay, so the pointer. So this particular pointer is going to have a deflection for you of it. So this deflection at steady state, what happens? The steady state represents the steadiness of the pointer. So at steady state, what we can write? At steady state, the deflection torque and the controlling torque both are equal. Okay, so the deflection torque formula is given by BINA, and controlling torque formula is given as Kc into theta. So now if I write the theta is equal to BINA by Kc, so theta is equal to BNA by Kc into I. So where B is a constant magnetic flux density, N is a constant number of turns, area of cross section is a constant, spring constant Kc. So then theta is proportional to I, we can say. Am I right or not? So if you observe, it is not in a position to detect the polar current. That means if the current is changing momentarily from positive to negative, this particular cannot sense. Okay, so this theta is proportional to I. Got it? Theta is proportional to I. So this is average. Always remember, DC is applied. So that means PMMC is best suitable for the average current. PMMC is best suitable for the average current. So this is one of the important expression. So from this, if you write the graphical representation, so if you draw the graphical representation, so on x-axis, on y-axis, if you take, so this is the deflection and the current. So if you write the graph is going to be like a straight line. The graph is going to be like a straight line. So that means the characteristics are obviously linear. So when the characteristics are obviously linear, the instrument is absolutely accurate instrument. So that's why the errors are very, very less with respect to readings. Uniform scale, we will call it as a uniform scale, not linear exactly, because everywhere you are going to get a straight line relationship. So that's why we'll call it as uniform scale. The PMMC will generate you a uniform scale, my dear. Got it? PMMC will generate you uniform scale. So these are the points that you have to understand. The deflection torque expression we have given, the controlling torque expression you have to remember, and in the exam we are going to get the questions on it. Okay, so basically PMMC is a measuring instrument which is used for the DC supply, which is having a permanent magnet. Under that, inside it we have a copper winding. Because of the interaction of the current passing and the magnetic flux, there is a deflection in the setup. That deflection is opposed by the springs controlling torque. At a steady state, when the deflection torque and controlling torque both are matching, there is a pointer steadiness. So that steadiness represents the magnitude of the current. If we calibrate that particular dial of the theta degrees in terms of the current, so we can easily use this scale for the DC current measurement. Now, if you see the errors this is most important. Every instrument is having certain set of errors. Of course, even though in GATE, this theoretical part is very rarely asked, but I suggest, because a set of instruments are there. When a set of, like today we are discussing the PMMC, next we will be discussing moving iron, next we will be discussing the dynamometer, energy meter. Each and every instrument is having certain set of errors. So if you see these errors, first thing, weakening of permanent magnets. Yes, yes or not? The magnet that you are using is made by Alnico material, but when you are using it for some years, then what happens? Obviously, because of the ambient temperature effect, there is a reduction in the magnetic flux. That is one point, aging of the temperature effects. Next thing, weakening of the springs. The weakening of the springs is also point. Springs, when they're compressing, that means whenever there is a deflection, the springs are opposing in this direction, right? So when it is happening, definitely what happens over a period of time, then what happens, that there will be having certain effect in their frictional effect. The springs may lose their stiffness. Every spring is having certain stiffness. That is what we call K. That stiffness, what happens over the period of time, if you use even the pen also, ballpoint pen, when you are typing like this, over a period of time, what happens is stiffness gets affected. Okay, so due to the temperature effect, the stiffness gets affected. Next, and most important, the moving coil. The moving coil is made by copper, right? So this copper is a metal. This copper is a metal. This copper metal is dependent on its temperature, right? So when metal is dependent on temperature, what happened? The temperature changes, its resistance gets changed. So that is also one point. Change of resistance of the moving coil with temperature. Change of resistance of the moving coil with the temperature. So these are the fundamentally three major things. Of course, this fourth point is just a detailed specification about the temperature versus resistance. When 1 degree Celsius rise in temperature reduces the strength of the springs by 0.04%, reduces the flux density in the air gap of the magnet by 0.02%. That means springs are affected by 0.0004% strength of the springs because of the temperature, and the magnetic flux density is affected by 0.02%. The magnetic flux density, the magnets. Okay, and next, overall deflection is changing by 0.02 per degree. Definitely the deflect. Why? Because theta is dependent on Bi, deflection is dependent on Bna na, but Bn, this expression. See this expression. Yeah. So this B is variable with respect to temperature. This stiffness is also going to be affected. Then ultimately what happens? The theta is also going to be affected. Okay. So this is what the errors. And one more error I want to add. It is of course these are the cause of errors, and the fundamentally the limitation of the PMMC. Basic limitation of the PMMC is what? Basic limitation of the PMMC is what? It cannot be suitable for the AC measurement. It's only suitable for the DC measurement. So next we will move for range extension. Even though whatever that PMMC is used as an ammeter, PMMC can be used as a voltmeter, because theta is proportional to I. This I comes from a set of voltage source. So obviously theta is proportional to V also. So PMMC can be suitable as ammeter, PMMC is also suitable as voltmeter. Now, but however, if you want to extend the range of the PMMC, how it is possible? Okay, so for that, let me take you the diagram of range extension. So if you see, this is the PMMC diagram. So this is the ammeter, and every meter is having internally copper winding. This copper winding is made by metal, so it is having length and width. So it is having some resistance. So this is the resistance. Okay. So now the point here is what I want to say. So this is current IM, and this is the meter resistance RM. Now, if you want to increase this current range from Im to I, that means suppose this is taken in milliamperes. I want to increase the range of this instrument from milliamperes to amperes. If I want to increase the range of this instrument from milliamperes to amperes, then what happens? If you attach a shunt resistance here, attach a shunt resistance like this. So this is the shunt resistance RSH. Okay. So now then what happens? There is a possibility of shunt current here. So shunt current ISH. So this I is split into two parts, Im and ISH. So this Im is fixed. How much current is passing through the meter? Rm is also fixed. So what I want to know is the shunt resistance. What I want to know is the shunt resistance. So what I want to know is the shunt resistance. How to find out the shunt resistance expression? If you see this particular box, this particular node, a Im Rm voltage and the voltage across this particular shunt, both are same, right? So these two voltages are same. So what I can write here, the voltage at the meter and voltage at the shunt, both are same. So voltage at the meter, I can write it as Im into Rm, and voltage at the shunt, I can write it as ISH into RSH. Okay, but if you see, this is unknown. We are going to attach a shunt resistance across the meter, so that what happens, we are going to get a good range of current. But what should be the value of this RSH? So for that we can write an expression here. The I can be taken as what? I can be taken as Im plus ISH. So these expressions you have to try to remember in the exam. If you want, easily you can derive also. So ISH can be written as I minus Im. Okay, I minus Im. So if you substitute that, I am substituting that. So what I am going to get here, Im and ISH. Im Rm is equal to I minus Im is equal to ISH here, right? So if I substitute, I want the shunt resistance, right? So shunt resistance can be taken as RSH can be taken as Im into Rm divided by ISH. So this ISH can be written as I minus Im. So this is Im into Rm, the whole divided by ISH can be taken as I minus. Okay. So now if I am taking this Im into Rm, the whole, if I am taking Im out, this will be I by Im minus 1. So Im gets cancelled. So this can be taken as M minus 1. Okay. M can be taken as the multiplying factor. So what I want to say here is, this particular meter resistance, RSH, we want the RSH, right? So please note down this formula. RSH is equal to Rm by M minus 1. So this is the expression. Okay. RSH is equal to RSH is equal to Rm by M minus 1. So you can remember the RSH equal to Rm whole divided by. So where this M is what we call as multiplying factor. Okay. So How to remember this formula? I will tell you the trick. In the exam, he will ask you the shunt resistance. Generally, shunt will be connected across. Yes or not? Shunt means it is connected across. It comes across this. So that means it will be parallel. Okay, na? It should be parallel. That means it should be at the bottom of something. Similarly, M should be at the bottom. So RSH is equal to RM by M. Just like RSH is here, M is here, where M is the multiplying factor. Please remember, M is the multiplying factor. Multiplying factor. What is M? M is the multiplying factor. So M can be taken as I by Im. What is M? Can be taken as I by Im. A single slide giving you I is the maximum current for which the range has to be extended. Im is the meter current. Okay. So this is one of the important area where regularly you are going to get questions. 1 mark questions or 2 mark questions. Regularly you are getting RSH. What is the shunt resistance to be added for a 1 milliampere PMMC ammeter which is having a meter resistance of 100 ohms? What should be the shunt resistance to be added so that its range can be extendable from 1 milliampere to 100 milliamperes? Okay, so that is the scenario. Next, let us move for voltmeter range extension. See, as I told you, PMMC can also be suitable as voltmeter. See, as of all of you know, voltmeter is also having just the same dial. The meter readings are changed in terms of the voltage. So, if you want to take the PMMC voltmeter range, so this is what I want to represent the PMMC. So this is our meter resistance. So now this is our M, RM, and for this we are going to connect a series resistor. For this we are going to connect a series. Okay, so what happens now? Let us see. See the voltage. Of course, if you can take this as a voltmeter, this voltage is what? Particular voltage is as the total current. What is the current traveling? Same current is traveling I. Whatever the current is traveling in the meter, the same current will travel in the series resistor. Now, question here is by connecting this series resistance, the range can be extendable. Because as you know, for this particular voltage drop, for example, if you take this as, Im, is a Vm hoga. Why? Because the meter current and meter resistance both are together. So the voltage across that meter will be this one, Vm. So this is our Vm. Okay. So this can be taken as, but whereas the same current is going here to here now. So the total voltage if you take, that means the total voltage if you take, total voltage. So Im into Rm, that is a Vm, I into total Rm plus Rsc, that is a V. Okay. So now let us write an expression for it. What is the expression? How to write that expression? See here. We take from that what I can write. Pm, let us take small letter. Taking the small letter, so one I will take. Okay, na? So Vm can be taken as I into Rm, same current passing. Whereas capital letter VSC, capital V can be taken as I into Rm plus Rsc. Rm plus Rsc. So now if I take the ratio of this V by Vm, what I am going to get? I into Rm plus Rsc, the whole divided by I into Rm. So this I gets cancelled. Okay. This I gets cancelled. So now if I separate this capital V by small vm is equal to 1 plus RSE by RM. This is 1 plus RSE by RM. If you take this V by Vm, just like in previous PMMC ammeter, we have taken as I by Im as multiplying factor. This is also multiplying factor. That's a multiplying factor of current. This is a multiplying factor of voltage. So if you take this as M, okay, M is equal to 1 plus RSC by. So from this here, so from this RSC by RM is equal to M minus 1. So the series resistance can be taken as RM into M minus 1. Series resistance can be taken as what? RSC taken as RM into. Got it? So this is the expression for the range extension required resistance for the voltmeter to increase its range, where Rm represents the meter resistance, M represents what? M represents what, my dear? M represents what? That represents a capital V by, alright? Everything correct? So this is the V by Vm, so which we call as multiplying factor. Call this as multiplying. So this is what we call as series resistance to attach or multiplying resistance. Multiplier resistance. So dear aspirants, please, easy to remember, just a second, easy to remember the series resistance as the series resistance, the resistance comes in series, right? The resistance comes in series here. So in a similar way, here the term M minus 1 term comes. Whereas that means after Rm it is coming. Whereas for the shunt resistance comes down. That's why M minus 1 is down. So these are the important formulas. So before entering into the numerical section, let me write the basic list of the formulas. 1 second. For PMMC, basic list of the formulas. For PMMC, formula shortly. Okay, fatafat. Important formulas. What are the important formulas? Let me write. Okay, what are the important formulas? Let me write. First, deflection torque is equal to Bina. That is one important formula in a box. Next, controlling torque is equal to Kc in theta. That is another one. So, at steady state theta and these are equal. So, theta is equal to Bina by Bna by Kc to I. So theta is proportional to I. These all are expected. Okay. Deflection torque and controlling. Next, when it comes to the shunt resistance can be taken as Rm by minus 1. Series resistance can be taken as Rm into M minus 1. So please make a note of this. Whereas here, M is the multiplying factor of currents, which is I by Im. Whereas here, this M is equal to capital V by. Okay, so these are the important formulas for the PMMC numerical questions, and most important, PMMC always measures the average value. So in the exam, we are going to get questions on waveforms. PMMC questions are expected on the waveforms. Sometimes you will give a waveform and you will be asking the question, what is the range of the voltage or range of the current. Okay, so in short, what I have explained in the first beginning of the session, just as a glimpse, I want to show you before moving. Constructional features I have covered in brief because we don't spend much time on the constructional features. Just you should know what are the components. Okay. So I told you in the beginning the types of instruments. Next I have given you the materials. So this is the magnet. So this is a coil. This white color is the aluminum frame. Okay, and this is the, if you want I will write here. So this is the magnet, and this one is coil, and this one is aluminum frame, and this red color is iron cylinder. These are springs made by phosphorus branch, and this is the spindle, and this pointer is also made by aluminum pointer. Dial theta is proportional. Okay, basic idea why that material is used, what is the reason. Okay, next, deflection torque expression, bina controlling torque expression, one of the important. Kc is the spring constant, there is Newton meter per degree or radian, majorly radians. Theta is proportional to average current. And next I have gone to the errors reason in the PMMC. The reason for the errors: permanent magnet gets weakened, springs gets weakened because of the temperature. And most important, range extension. For range extension I have given you the shunt resistance expression, and I have given you the range extension voltmeter system. So with this, please take this as a reference now. Now let us enter with this knowledge. Let us enter immediately to the problems. Okay. So now we will move on to the PMMC related gate level problems. Now we will start some numerical problems on PMMC. This is the first question. Question was asked by IIT Madras in 1991. The current I of t passing through 10 ohms resistor is shown in the figure, as shown in the figure B. So this is the circuit diagram. There is a resistor, in this current is passing. Across this we have connected a DC voltmeter, and the current waveform is this 12 amperes, 5 amperes. That means the current is switching 0 to t time period, it is maintaining 12 amperes, and between t to 2t the time is between the t to 2t time it is coming down to 5 amperes. Again 2t to 3t it is switching to 12 amperes. That means it is switching between 12 and 5. So first of all we need the DC voltmeter, that is PMMC. So PMMC measures the average voltage, yes or not? So the voltage across the resistor, the V average can be taken as I average into resistor. So what is I average? If you see, the average current can be calculated as two ways. First is area under the curve by the time period. So I average for these particular waveforms, area under the curve, divided by the total time. So let us take the area under the curve. First, this particular area, if you see, so this is the rectangle, 0 to t is the time and 12 is the length. So this is 12 into t plus, next one, this area. So this is 5 into 2t minus, okay, so divided by the total time period is 2t. So if you check, so this will be 12t plus 2t minus t, this is 5t, so 5t by 2t, so 17t by 2t, that is coming as 8.5, tt gets cancelled. So this I average is 8.5. The average current is how much? 8.5 amperes. So then we can calculate the V average. V average is equal to I average into resistance. So that it can be taken as 8.5 amperes into resistance. That resistance is 85 10 ohms. 85 volts is the right answer. It is a NEAT type question. There are no options, so we have to give the exact answer. So it is a fill in the blank question. So don't miss such type of questions. So the right answer here is 85. Okay. Or else another method also we can do. The I average directly we can take. The pulse is switching between the 12 and 5. So the I average can be directly taken as 12 plus 5 by 2. So that is 17 by 2. That means 8.1 amperes. That also can take here. Okay. So this is what simplest problem. So don't miss such type of problems. In the GATE, many number of times this waveform related questions are coming. So the right answer is 85. Okay. Let us move for the next question. This is a question number 2. Question number 2. A 0 to 10 milliamperes PMMC ammeter reads 4 milliamperes in a circuit. Its bottom control spring snaps suddenly. The meter will now read nearly that. See, as I told you, if you see the PMMC diagram, as I told you the PMMC diagram, it contains, as I told you the PMMC diagram, it contains magnet, north pole, south pole, and in the between there is a spindle, so this is a spindle. Okay. Here the point is we are having the copper winding here, not drawing the full diagram. This is a copper winding. This copper winding is connected. Copper winding is connected springs. Copper winding is springs. So these are the springs. Okay. The way how these copper windings are connected. So this is a passage of the current, right? You can take the current anything like this. So if you take the current like this, so this is our, yeah. So this is a north pole, this is a south pole, this is a copper winding. So this is a current passing. Okay. So this is a current direction. Current is going like this, yes or not? So if the bottom spring snaps suddenly, what happens? There is no passage of the current because the springs are current leading, okay na, current leading type. So they will allow the current to pass through. Okay na? The springs are current leading type, so they will allow the current to pass through. So suddenly if the bottom spring snaps away, then what happens? So this particular bottom spring snaps away, then definitely the current will become zero. When the current, this spring snaps means there is no current, there is no passage of the current. When there is no passage of the current, there is no question of deflection torque. The deflection, because there is no interaction of the magnetic field, so the current becomes zero, means becomes a good question, conceptual question, because current springs are the part of the current passing. Current is entering through the springs. So the right answer goes to 0 is the. Let us go for the next question. Yeah. Question number 3. The scale of a voltmeter is uniform. Its type is dash. Option A, moving iron. Option B, induction type. Option C, moving coil permanent magnet. Option D, moving coil dynamometer. Okay. So if you see PMMC scale, we have discussed already. PMMC scale, theta average is directly proportional to the current. Sorry. Theta is proportional to average. Theta is proportional to I average. That means if you take the scale, so if you take the scale like this, so this is the scale which is uniform. So this is the nature of the PMMC. Frankly speaking, even though I have not covered other instruments, just I want to give you some information. See, for the PMMC, deflection torque is binar, controlling torque is equal to Kc theta. So finally, when steady state, if we take theta is proportional to I. Whereas the moving iron instrument, the deflection torque is equal to 1 by 2 I square E L by d theta. Controlling torque Tc is equal to Kc into theta. So theta is proportional to I. So this is I square. So the scale is not uniform. The scale can be non-uniform. At the lower values, it will get crowded. At the middle, it will get some linear, and at the spacious values, when you go for far extent, the scale will be not linear. So that's why this is not uniform. Similarly, the dynamometer also, if you take the dynamometer, the deflection torque is I square into dm by d theta. Controlling torque Tc is equal to Kc t theta. So theta is proportional to. So these all are non-uniform scales. So this is non-uniform. This is also non-uniform. So this is only uniform. So what we are going to get a uniform. What we are getting is a uniform scale. The uniform scale is the nature of the PMMC. That is an advantage of the PMMC. So we can go for the option, which is the right answer. Moving coil permanent magnet. Option C is the right answer. The right answer. Permanent magnet moving coil is the right answer. So always okay. Now let us move for the next question. This is question number 4, asked by IIT Kanpur in 1995. What is this? 200 volts full scale PMMC type DC voltmeter having figure of merits 10 kilo ohms per volt and 20 kilo ohms per volt are connected in series. The series combination can be used to measure a maximum DC voltage of dash volt. First of all, what do you mean by figure of merit? FOM, which is called figure of merit. Figure of merit means it is the sensitivity of the voltmeter. Sensitivity of voltmeter. What we call as sensitivity of the voltmeter. Okay. So if you see the units of the sensitivity, that means what? This voltmeter is going to be connected across a particular resistor network. So when the voltmeter is connected across a resistor network, voltmeter is nothing but PMMC, that's internal resistance is their RM. Okay. So the voltage across that particular resistor will be what? This parallel combination. So this RM will be in parallel to that R2. So R2 RM by R2 plus RM, some R equivalent will come. And if we want to find out the voltage across that V2, so what is that V2? This resistance by the total resistance. So if you see now, that means how much resistance is offered to get a voltage. To represent particular 1 volt, how much resistance should be offered? You understand? To represent one particular volt, that means to measure 1 volt, how much internal resistance that voltmeter will offer. So that is what we call as sensitivity. Sensitivity is also in different way we can express. If you see the units of sensitivity, that is kilo ohm per volt, yes or not? So this is what per unit voltage, how much resistance offered by the voltmeter. If you take the inverse of the sensitivity, suppose 1 by sensitivity, if you take, what you are going to get? That means 1 by kilo ohms per volt. 1 by kilo ohms per volt means what? That is volt per kilo ohms. That is nothing but this. You take this is the resistance, this is the voltage unit, and this is the resistance unit. So that is nothing but current. So 1 by sensitivity is nothing but that is the full scale deflection current. That means how much resistance should be offered by the particular voltmeter to get the full scale deflection. When it deflects full scale, the full scale deflection current, if you want to enter the full scale deflection current, it has to be enter into your particular voltmeter. What should be the resistance offered per unit voltage? That is what we call as sensitivity. So this is what we call as full scale deflection sensitivity because the units are ampere. Okay, so inverse of sensitivity what we call as amperes. That is what we call as full scale deflection. Okay, so please make a note of this point. Figure of merit is also called sensitivity of the voltmeter. As per the units we can understand, to represent or to measure 1 volt, how much resistance is offered by the voltmeter. So that is what we call sensitivity. Inverse of that sensitivity is nothing but the full scale deflection current. Now if you see this question, 200 volts full scale PMMC type DC voltmeter. So there are 2 voltmeters, 1 voltmeter. Okay, so the full scale value here, you see the full scale value is 100 volts. 100 volts. Also 200 volts full scale PMMC type DC voltmeter having a figure of merit 10 kilo ohms per volt. So that means sensitivity of this S1 10 kilo ohms per volt. Okay, and S2 also same. Sorry, S2 is 20 kilo ohms per volt. Is 20 kilo per. Both are connected in. So if you see now, the full scale deflection current for the first voltmeter is nothing but 1 by sensitivity. So that is 1 by 10 kilo ohms per 1 volt. Okay, how much you are going to get? 1 by 10 kilo ohms per volt. That means 0.1 kilo means milli, 1 ampere. So this is the I scale deflection current 1. Means to display 100 volts, it requires a full scale deflection current of how much? 0.1 milliampere. Next, the full scale deflection 2, here it is 1 by S2, and if you take the inverse of this 1 by 20 kilo ohms per volt. So that means 0.05. Yes or not? 0.05 milliamperes. So this is the second full scale deflection current. Second full scale deflection IFSD1, IFSD. That means what? To show 100 volts full scale voltage, that is possible for this voltmeter for a full scale deflection current of how much? For a full scale deflection current of how much? 0.1 milliampere. But whereas this, there is a full scale deflection current of 0.05 volt milliamperes. When 2 voltmeters are in series, generally will take the minimum current into consideration. Why? Because the second voltmeter is going to have a good deflection, full scale deflection for a current of 0.05 milliamperes. Okay, so now both are connected in series. Keep this in mind. When both are connected in series, see here, what is the internal resistance offered here? For 1 volt 10 kilo ohms means for 100 volts it will be how much? See, for this particular one, for 1 volt 10 kilo ohms means for 100 volts For 100 volts, 100 into 10, so that means it is a 1000 kilo ohms. So this resistance is the 1000 kilo ohms, the first voltmeter. You understand? For 1 volt 10 kilo ohms resistance offered means for 100 volts it will has to offer 1000 kilo ohms. Next, sensitivity 2, if you take for 1 volt 20 kilo ohms means for 100 volts it will offer 100 into 20, that means 2000 kilo. Now these are the internal resistances offered by this particular voltmeter at what condition? At full scale deflection. When two voltmeters are in series, we expect the minimum current is the expected for giving the full scale deflection. Okay, why? Because out of the two currents, for the smallest current of 0.05 milliamperes we are getting the full scale deflection. So if you take the full scale deflection as IFS2, that is 0.05 milliamperes going. Okay, so 0.05 milliamperes. So what happens now? If you see, 0.05 milliamperes, if you see what happens now, so this will be what now? 0.05 milliamperes means, so 0.05 milli. What is the question asked? The question asked is maximum DC voltage. So how much it will be? 0.05 into 1000 plus 2000, means the kilo and the milli gets cancelled. So this will be 3000 into this, so 150. So 150 volts is the much? 150 volts is the. Okay, so two voltmeters are in series. Out of that, one particular voltmeter is getting a full scale deflection current for 0.05 milliamperes, and the internal resistance are calculated according to their sensitivity. So we are going to get how much now? Get how much we are getting? So the right answer for this question here is a DC voltage of 150 volts is the right answer. Please make a note. Very good. Very good. The only thing you have to understand is the inverse of sensitivity is the full scale deflection current. Okay, IFS. I hope all of you followed. Next question. Question number 5. This question was asked by Bangalore, ISC Bangalore in 1996. What is the answer? An advantage of permanent magnet moving coil instrument is that it, option A, is free from frictional error. Option B, it has high torque to weight ratio of the moving parts, very clearly given in the brackets. Very good conceptual question. Has low torque to weight ratio of the moving parts. Next, can be used both AC and DC. First, try to eliminate the wrong options. Question asked is PMMC. So PMMC means it is suitable only for the DC current or DC voltage measurement. So can be used both AC and DC. So option D wrong. D can be eliminated. Okay, option D can be eliminated. Next, it is free from frictional error. No, every instrument is having the moving parts. Wherever the moving parts are, there is a possibility of friction. So this is also wrong. Next, now the torque to weight ratio. So what do you mean by torque to weight ratio? Torque to weight ratio, weight ratio of moving parts. Weight ratio of moving parts. If you see the PMMC, in the PMMC, the moving part is what? The moving part is a pointer, right? So this pointer is made by aluminum. So aluminum is a lightweight. Aluminum is a lightweight. I think all of you know aluminum frame and aluminum that base. The lightweight. So when weight is less, so weight of the aluminum. Why? Because moving part is nothing but aluminum, right? The moving part is nothing but the frame. Inside the frame there is a coil, copper coil. But the moving part is aluminum, so the weight of the aluminum will be less. When weight of the aluminum is less, then definitely the torque to weight ratio, this will be, so this is less now, more. So the moving parts are maintaining high torque to weight ratio. Very good question, conceptual question. So option B is the right one. Torque to weight, weight is in the denominator. Weight is in the denominator. He is asking the weight of the moving part. Here the moving part is the pointer. The pointer weight is aluminum made. So definitely its weight is less. So option B the right answer. Next question, again the question number 6. Question number 6 asked by IIT Delhi in 1998. So a DC voltmeter has a sensitivity. Again the figure of merit is given. A DC voltmeter has a sensitivity of 1000 ohms per volt. That means to represent 1 volt, it offers a internal resistance of 1000 ohms required. When it measures half of the full scale in 100 volts range, the current through the voltmeter is dash. See, first of all, this is the voltmeter diagram. So the full scale is how much? 100 volts. 100 volts is the full scale value. Okay, now half of it, the half, a DC voltmeter sensitivity, and measure half of it means 50 volts. So half of it will be 50 volts. So first of all, what is the sensitivity given? Sensitivity is given as 1000 ohms per volt. Okay, now 1000 ohms per volt. So what is asking? When it measures the half of the full scale, the current through the voltmeter is asking. So first of all, suppose what is the full scale deflection current for this particular sensitivity? If you check, that is 1 by sensitivity. That means 1 by 1000 ohms per volt. Okay, so that means 0.001, sir, not 0.001 ampere. That means 1 milliampere. Am I right? 1 milliampere is the full scale deflection current allowed through this voltmeter to give 100 volts. That means to take this as a voltmeter, 1 milliampere is the current full scale 1 milliampere is the current to give full scale deflection. What is the full scale deflection? The full scale deflection is 100 volts. But now he is expecting for half of the full scale. He is expecting for what? Half of the, for 100 volts, if you require 1 milliampere, definitely for 50 volts, how much? 0.5 milliampere, half of the. So he is expecting how much? 0.5. Because for 100 volts 1 milliampere, definitely for 50 volts, the current required is 0.5 amperes. Option C is the option C, 0.5 milliamperes is the, got it? Conceptually very, very excellent question. 0.5 milliamperes. Let us move for the next. 0.5 milliamperes. Move for the next. A moving coil galvanometer, question asked by IIT Delhi 1998. A moving coil galvanometer is made into DC ammeter by connecting dash. So this question is related to what? The PMMC as an ammeter. What is the diagram of PMMC as an ammeter? So this is the meter current IM and it is having some internal resistance. So this is the meter resistance RM and across it we are having the shunt resistance. This is what our shunt resistance, right? So the shunt resistance must be low so that it can attract more shunt current. Okay, a moving coil galvanometer is made into DC ammeter by connecting a low resistance. By connecting what? By connecting a low resistance. Connecting a low resistance across the meter or high resistance in series? No, this is for voltmeter. Okay, a pure inductance. There is no question of inductance here. A capacitor is also wrong. So right answer is a low resistance across the. That's what shunt. All the shunt elements must be low so that they can be connected across so that maximum current is. Chalo. This is a very good question. And theoretically they are asking conceptual questions. Keep that in mind. Next. Yeah. Question number 8. So question is again on the figure of merit, I think. So question number 8. So this asked by IIT Delhi in 1998. 200 microamperes full scale PMMC meters are employed to construct a 10 volts and 100 volts full scale voltmeters. These meters will have a figure of merits as dash. So what is the question? 200 microamperes full scale PMMC meters. So this is one PMMC meter. This is one PMMC meter. What is the full scale deflection current? So this full scale deflection current IFSD is how much? 100. This is how much? 100 microamperes to give a full scale voltage. What is the full scale voltage for this? 10 volts. For the 200 microamperes full scale PMMC meters are employed to construct a 10 volts and 100 volts. Second one is 100 volts. And what is the full scale deflection current entering here? Same full scale deflection current here also. Okay. Question asked is these meters will have a figure of merits. Definitely. What is a figure of merit? Figure of merit is nothing but to represent 1 volt, how much resistance is required by the voltmeter, or the full scale deflection is given na. So what is the sensitivity of this one? Sensitivity of this one is equal to 1 by IFSD. So this is coming as 1 by 100 microamperes. So this microamperes I can write as V is equal to IR, I is equal to V by R. So I can write as volt per ohm. That means 100 micro means how much here? 10 square into 10 power minus 4. 10 square and 10 power, this is 10 square, this is 10 power minus 6, 10 power minus 4. And it goes to the top 10 power plus 4. 10 power plus 4 means 10 K. And ohm per volt, 10 kilo ohm. And S1 is equal to S2 because this also full scale deflection current is 100 microamperes, 10 kilo ohms per volt. Got it up? Yes. So 10 kilo ohms per, both are having same full scale deflection current. Okay, so the right answer goes to 10 kilo per volt. Both are same. Okay, because both are getting the same full scale deflection. Question number 8. So let us go for the next question. Question number 9. Question number 9. This question was asked by IIT Kanpur in 2001. IIT Kanpur. Okay, a 100 microamperes ammeter has an internal resistance of 100 ohms. For extending its range to measure 500 microamperes, the shunt resistance required is of dash. So first let us draw. So this is our meter current IM. This is our RM. And here comes shunt resistance. So this is the I. What is the question asked? Check. So this is diagram of PMMC as ammeter. PMMC as a diagram is PMMC. A 100 microamperes ammeter. So this IM is equal to 100 microamperes. Has an internal resistance of 100 ohms. So this RM is equal to 100 ohms. For extending its range to measure, so he wants to extend the range from 100 microamperes to 500 microamperes. What is the shunt resistance? Already we have discussed. Shunt is connected down, the M-1 also will connect down, I think in the just before lecture. So I can write RSH is equal to Rm by M-1, where M is the multiplying factor of the current. So what is that? I by Im. What is I? What is I? I is the range for which you want to extend. Im is the meter current. So minus 1. Rm by Im, I by Im minus 1. So the shunt resistance, the Rm, what is the Rm? This Rm is 100. The total divided by I is 500 microamperes. Nice. By Im is 100 microamperes. So I can wave off this microamperes. 500 divided by 100 minus. So I will take, okay, options are very close, so definitely I will use calculator. So this is 100 by 500 by 100, that means 5 minus 500 microamperes, 100 microamperes, microamperes cancel, 5 minus 1 is equal to 4. This will be coming as 25 microamperes. So the right answer for this, is resistance, right? So right, micro, this is micro cancel. So 5 minus 1, 4, 100 by 4, 25 ohms. Right answer for this question here is C. C is the, so don't miss formula based questions, easiest questions, formula based questions. Okay, these questions under the rectifying instruments. Let us practice more questions on range extensions. Let us see this question again. A galvanometer with a full scale current of 10 milliamperes has a resistance of 1000 ohms. The multiplying factor, the ratio of measured current to galvanometer current of a 100 ohm shunt with this galvanometer is dash. See what is asking, try to understand. Please, always I suggest to draw the diagram, otherwise you will get confused. So this is current. So current means he is expecting ammeter. So this is the Im. So this is the Rm. And this is our RSH. And this is our I. A galvanometer with a full scale current of 10 milliamperes. So this is given as 10 milliamperes. Has a resistance of 1000 ohms. So this meter resistance is how much? 1000 ohms. The multiplying factor is asking. When a shunt is given, so shunt is given, my dear. So shunt is. So in this situation, what I can write? RSH is equal to Rm by M minus 1. Shunt is given, so we have to find out the simple calculate. So this is 100. RSH is 100. Rm 1000. Sorry. Yeah. M is asking, right? Yeah, we have to calculate the M. 1000 by M. M is 11, right? It's 11. So the right answer. Okay. 11th question, answer is next. Yeah. Question number 12. This question is again a conceptual question. IIT Madras in 2003 it was asked. How to answer this question number 12? Go through it. See, theoretical questions are conceptual, and nowadays there is a possibility of expecting MSQ also, multiple select questions also. Okay, So keep in mind. A manganese swamp resistance is connected in series with a moving coil ammeter consisting of milliammeter and a suitable shunt in order to dash. See, the question is related to moving coil ammeter. First of all, in moving coil ammeter, we are having the moving coil is made by copper. Copper is a metal. Definitely, whenever there is a temperature effect, its resistance is also going to be affected. A manganese swamp resistance is connected in series with a moving coil ammeter consisting of a milliammeter and a suitable shunt in order to dash. Option A, minimize the effect of temperature variation. Option B, obtain large deflecting torque. Option C, reduce the size of the meter. Option D, minimize the effect of stray magnetic fields. So how to understand this question? See, if you take the PMMC as ammeter, I will take the diagram like this. So this is my meter and this is the meter resistance inside. And now I am attaching a swamp resistance. And this is the total current. And across we are having one shunt resistance. Okay, let us see. So this is our shunt resistance. So this is our meter IM with its internal resistance is also there. IM with RM. Now, what is this? I will explain. This meter resistance RM, which is the meter resistance RM, this is made by copper, right? Copper. Copper is a metal. As the temperature changes, what happens to the resistance of the copper? It also changes accordingly. Because it is a metal, positive TCR characteristics. Positive TCR characteristics. So as the temperature increases, resistance increases. As the temperature decreases, resistance. So it is having the positive TCR characteristics. So that will reflect in the copper. That will be reflecting in the. Okay. So now obviously then what happened? The shunt resistance is there. So now this is the current I. So this is the current ISH and this is the current passing through the meter, right? I. So whenever there is a change in temperature, definitely this resistance changes, this meter passing current also changes. So to nullify that effect, I am using another resistor called manganese resistor. So this is what we call as swamping resistance. The swamping resistance is generally made by the material manganese. Is made by material manganese. This manganese is having zero TCR. Okay, so that means what? Its resistance is unaffected. Okay, its resistance is unaffected by the temperature. So how much the adjustment is happening here because of the temperature, that much is added here. How much a loss of things are happening here, that much is added here. And the swamping resistance having 20 times higher resistance value, 30 times higher resistance value, then what happens? Definitely the current proportion will remain the same like before. Because accordingly RSH, according to this R swamp, RSH also will change. Why? Because previously what is RSH? Previously RSH was RM by M minus 1. But now what is the RSH? Now the RSH will be RM plus R swamp by M minus 1. So shunt resistance is affected. When that means shunt resistance that to be added is also changing according to the swamp. And this copper winding resistance compared to swamp resistance will be nullified. I mean very less. Why? Because this swamping resistance is high. So accordingly you will make the RSH. So then what happens, this ISH and IM again will be retaining to the values which are not affected by the temperature. That means before temperature what was the reading, when temperature changes has happened the reading was affected. So these effects are again nullified back to the previous. So swamping resistance is utilized in adjustments of nullification of the temperature effects. That is advantage. So that is done with the manganese material. So manganese material is having the zero temperature coefficient of resistance. That means whatever may be the temperature changing, its resistance is unaffected. So definitely that resistance is going to be added to the series resistors of the coil. Accordingly the shunt resistance gets changed. So accordingly the current proportionals are not altered like previous. Okay, when temperature changed at that time currents are altered, but now when you attach the manganese resistance again it comes back to the normal adjustment. So what is the concept? It will obtain large torque. No, this is the wrong answer. The wrong answer. Reduce the size of the meter, wrong. Magnetic fields, wrong. So it's related to temperature. Remember always manganese, these all are related to temperature. Okay. So temperature effect is there in all the meters, because wherever the copper is there, the moving coil is made by the copper, definitely have this effect. Definitely we are going to have this particular effect. Okay, chalo, let us move for the question number 13. This question was asked recently, IIT Delhi 2004. Question was asked in IIT Delhi, question number 13. A moving coil of a meter has 100 tons. 100 tons N. So that means N is given. Question is related to PMMC working formula. 100 tons are there. Length and depth 10 mm cross 20 mm respectively. That means length and breadth is given as 10 mm cross 20 mm. It is positioned in a uniform radial flux density of 200 millitesla. So B is given, that is 200 millitesla. The coil carries a current of 50 milliamperes. The current carrying is how much? 50 milliamperes. The torque on the coil is dash. How to solve this? So if you see, question is related to PMMC torque. Question is related to PMMC torque, the deflection torque. So what is the expression for deflection torque, dear? So deflection torque is given as BINA. So here if we check, P is given as how much? P is given as 200 millitesla. So that means 200 into 10 power minus 3 Weber per meter square. Next, current is given as 50 milliamperes. So 50 into 10 to the power of minus amperes. Next, number of turns is equal to 100. Number of turns is equal to 100, and area of cross section length into breadth, that is can be taken as 10 into 20 mm. If you convert into meters, 10 to the power minus 3, 10 to the power minus 3, so 10 to the power minus 6. And this meter square and this meter square gets cancelled. Okay, and Weber, ampere, tons, all these things. That is nothing but torque, Newton meter. So I think you can get 10 to the power minus 3 gets adjustments. So this 10 power minus 3, 10 power minus 3 gets cancelled. So 1, 2, 3, 4, 5, 6 gets cancelled. Sorry. I will remove this meter. Calculate 10 power minus 3, 10 power minus 3. Okay. 100 millitesla to 10 power minus 3. Current is 50 milliamperes, 15 10 power minus. Sorry. It's calculation. Okay, 1, 2, it's gone. 1, 2, 3 is gone. So 10 power minus 6 will be there. So 2 into 5, 10, 10 into 20, 200. So I'm getting 200. Am I right? So 200 micro Newton meter. Why? Because I'm having 10 power minus 200 micro Newton meter. The option A. The 200 micro Newton. 200 micro. That's deflection torque formula. You should be careful about that units, bina units. Sometimes he will give area in millimeters, centimeters, so units can be cancelled. Yeah. Let us move for this question number 14. A PMMC voltmeter is connected across a series combination of DC voltage source V1 is equal to 2 volts and AC voltage source 3 sin 40 volts. So as you know, PMMC measures the DC. Simple question. If you want, you can draw the diagram. So there is a DC voltage and there is a AC voltage. So across this, our PMMC is connected. Diagram. PMMC means only DC. Okay, na? So obviously, what is the right answer? PMMC, don't miss the question. So right answer goes to the DC. Okay. Next. Question number 15, I think you can answer. This is 15. Huh? Number 15. A DC ammeter has a resistance of 0.1 ohm and its current range is 0 to 100 amperes. If the range is to be extended to 500 amperes, then the meter requires a shunt resistance. So as I told you, formula, IIT Bombay. See, I don't want to repeat the same concept, but the questions are repeated. You can practice. I will give you the formula. What is the formula? The shunt resistance formula RSH is equal to Rm by M minus 1. Okay, na? So this M is equal to I by Im. This M is equal to I by Im. So what is the Rm meter resistance? A DC ammeter has a resistance of 0.1 ohm. Fatafat is 0.1 ohm divided by, and its current range is 0 to 100 amperes. We want to extend by 500. So this 500 by 100. So 4. So 0.1 by 4 means 0.02. So the right answer goes to, don't miss, option C is the answer. Don't miss the question. Okay, very simple question. Always try to practice the formula. Okay. Yeah, this question number 16, which was asked by IIT Kharagpur 6. A current of minus 8 plus 6 root 2 sine omega t plus 30 degrees is passed through 3 meters. One is the center 0 PMMC. Okay. True RMS meter, yes. Another one is moving iron instrument. Very good. If you see one point here, this will measure the DC. This will measure the DC. This will measure the AC as well as the DC, and this will measure the AC. That's so now what is the current? The current passing current. How to solve this question? And one of the important point here is center PMMC. Center PMMC means what? This is center 0. So this side positive. So this side negative. It is center 0 means it can find out the negative current, I mean negative magnitude current of VC. Suppose if you take the square pulse, positive pulse and negative pulse, okay, negative magnitude and positive magnitude also, it's a DC current, negative DC current, negative side. But whereas true RMS and moving iron, they will measure the RMS value. So what is the point? PMMC, so actually this question includes other meters also. So you take the I, how to calculate this? You take for PMMC, PMMC takes only I average. I average means what? Square root of minus 8 whole square. So that means it is minus 8.64, that means 8 amperes, right? But the point here is it is a center 0. Center 0 means it can represent plus 1 to plus 8. It can also go to minus 1 to minus 8. So that's why it is also representing minus 8 amperes. So because it is a center 0, center 0 PMMC means it can detect the positive amplitude current and it can represent the negative amplitude of current. That's why suppose he has not mentioned the center 0, the right answer will be 8 amperes. But as he has mentioned, we can take this as minus 8 amperes. Next. What about these other things? True RMS. True RMS means current measured by the true RMS. That is RMS current. RMS current means what to do? Minus 8 whole square plus what is the RMS point? This point 6 root 2. 6 root 2 by root 2. So root 2 gets cancelled. So I think this is 10. Similarly, other moving iron instrument also RMS. So moving iron, that is minus 8 whole square plus 6 root 2 by root 2. That is right answer will be minus 8, 10, 10. So the option goes to 8, 10. C is the right one. Minus 8, 10, 10. Option C. So please be careful. It is not plus 8. So, sir, okay, other options are not matching. But 10, 10 is there. Suppose if you have 8, 10, 10, definitely could have given the answer. It is center 0 PMMC, dear. Center 0 PMMC means take positive and good question. Again, this question is related to shunt. फटाफट कर सकते. An ammeter has a current range of 0 to 5 amperes. That means IM is 5 amperes. Its internal resistance is 0.2 ohms. RM is 0.2 ohms. In order to change the range to 25 amperes, that means I is 25 amperes. We need to add a resistance of dash. So ammeter na, so is asking the RSH. Fatafat. RSH is equal to RM by M minus 1. So RM by I by IM minus. RM is given as 0.2 ohms. Right? I is how much? 25 by 5 minus 25 by 5, 5 minus 1, 4, 0.2 by 4, 2 by 40, 2 by 40 means 2 by 20, 1 by 20 means 0.05 ohms, shunt. So 0.05 ohms, the right answer. What is the answer? Going to get 0.05 ohm. That is the answer. And always shunt means parallel. Option T is the mistake, you can check it. 0.2, I is 25, I by M 5, 5 minus 4, 0.2 by 4, 2 by 40, 1 by 20, 0.05. Yes, perfect. 0.05. These questions we'll discuss at the rectifying instrument. Yeah. Question number 19. This is question number 19. A periodic voltage waveform observed on oscilloscope across a load is shown. Okay, so this is the current passing through a load and it is connected to PMMC. As I told you, PMMC measures the second. Yeah, this is a voltage. PMMC voltage waveform. It's not a current waveform, PMMC voltage waveform. So if you see 0 to 10, one waveform, and 10 to 12 another waveform, 12 to 20 another waveform. So how to do it? V average we can calculate. There is a lengthy method by taking 0 to time waveform, 0 to 10 what is a waveform, 10 to 12 what is a waveform, 12 to 20 what is a waveform, and taking the average of it will take time. So we'll go for the best simplest method, area under the curve by time. So what is the area under curve, my dear? Here first one 0 to 10, that is half 10 into 10. Next, plus this is the this is minus 5, 2, minus 5 into 2 plus 20 minus 12, 8 into 5 plus 5 into whole divided by, okay, 20 milliseconds. Half 10 milliseconds, 10 volts, minus 5 volts, 2 milliseconds, plus 20 minus 12, 8 into 5 volts. So if you simplify, how much you are going to get? Check it. This is milliseconds. This is milliseconds. This is milliseconds. So milliseconds, volts, milliseconds gets cancelled. The units are volt, millisecond, millisecond gets cancelled. Okay. That is the area under curve, half into 10 into 10 minus this distance is 12 minus 10, that is 2 milliseconds, and this is minus 5. How much are you going to get? 10 into 10, 100 by 250. This is minus 10, 40 plus 40, 80, 80 by 20, 4. So answer is coming 4 volts. Cut off it. Other method is there by taking 0 to 10 seconds ramp waveform ka equation, 10 to 12 square waveform ka equation, 12 to 20 again square waveform ka equation, and taking the average 1 by t integration of 0 to t. That all you can do it. In network theory you could have got it, mathematics also you could have got it, but I suggest the time saving method for this particular way. Okay. This question What interesting, question number 20. The DC current flowing in a circuit is measured by two ammeters. One is the PMMC, other one is the electrodynamometer type. Okay, so to measure the current is using the two instrument. One is the PMMC, other one is the dynamometer type. Connected in series. The PMMC contains 100 turns the coil. The flux density in the air is 0.2 Weber per meter square, and the area of this coil is 80 mm square. The electrodynamometer ammeter has a change in mutual inductance of 0.5 millihenry per degree. The spring constants of both the meters are equal. The value of current at which the deflection of the two meters are same is dash. Here I want to tell you, of course, this question is one second. This question requires electrodynamometer torque formula also. So first let me write here. For PMMC, the deflection torque formula is INA, and controlling torque formula is KC. Okay, so at steady state, deflection torque is equal to controlling torque. So BINA is equal to AC theta. So theta is equal to DNA by AC into I. So this is the expression. This is the expression for PMMC. Okay, similarly, for moving iron, sorry sir, not moving iron, for dynamometer, next coming chapters will get. For dynamometer, deflection torque is given as I square dm by d theta. Controlling torque is equal to Kc theta. So at Td is equal to Tc if you take I square into dm by d theta equal to Kc theta. So theta is equal to I square by Kc to dm by. So this is the expression here. Mutual inductance constant. Basically, it works on the mutual inductance. These are two expressions. Very good question. Actually, this type of questions necessary. Simply asking on one instrument formula, but here comparing two currents. Okay. So what is the question here? Let us see. The DC current flowing in a circuit is measured by two ammeters, one by PMMC. So let me write the PMMC data first. We write the PMMC data. What is the PMMC data he has given? 100 turns is there. So N is equal to 100. The flux density is 0.2. And the area of the coil, area is 80 mm square, that is 80 into 10 power minus. The electrodynamometer. Okay, now let us take the dynamometer data. Let us take dynamometer data. Okay, what is the dynamometer data? He has given the dm by d theta directly. Dm by d theta he has given as 0.5 millihenry per degree. Very good. Okay, nice. The spring constant for both the meters are equal. So this and this same. What is the value of the current at which deflections are the same? That means what? If you take this deflection as theta 1, if you take this deflection as theta 2, you take this deflection as theta 1, and if you take this deflection 2, is asking. Okay. So theta 1 is equal to theta 2 if you take it. If you take what current he is asking na, so theta 1 and theta 2 both are same. Second, let me take one more slide. So if you take theta 1 is equal to theta 2, deflections are equal at a current I. Okay na, at a current I. So bina theta 1 is equal to bina Bn A by Kc into I, and theta 2 I square by Kc. So these two currents are same now. I square by Kc by dt. Two currents are same. So now what happens, dear? Kc gets cancelled. Kc gets cancelled. One current gets cancelled. So Bna by Pm by theta. Is it right? Oh, font is not clear. In the pen. What I can write? Pna by Pm by so now we can write what is the expressions. B is given as how much? B is given as 0.2. Number of turns is given as 100. Following, number of turns is given as 100. Just let me increase the font. The area, the area I can take it as 80 into 10 power minus 6. 80 into 10 power minus whole divided by dm by d theta. dm by d theta, that is given na 0.5 millihenry per degree. So that is 0.5 into 5. Check it. Very good question. Point 2 into 100 into 80 divided by 0.5. 3.2 microampere. 0.2 microamperes. Am I right? 0.2 into 100. To amperes, I think. 3.2 ampere. Yes, 3.2 amperes is the very good question. That means both are expecting to give same deflection at a current of 3.2 amperes provided their spring constants are equal. Got it? Are you clear? Hello? Provided their things are. Let's go for one more question. For 21. A DC voltage with a ripple E of t. So V of t is given as expression 100 plus 10 sin omega t This sign here. 5 sine measured by moving coil and also moving iron. Okay. If PMMC measures for this, what is the V1 reading? Show reading of V1. See this instrument, this particular current is measured by the two instruments. One is the PMMC, other one is the moving iron. If PMMC measure V1, V1 means average value, that is 100 volts. Whereas moving iron measures the RMS, right? That is V2. So what is the RMS of this value? 100 square plus 10 by root 2 square plus 5 by root 2. How much you are getting? Please check it. $100.312, getting us 100 point. Okay, so now question asked is the value of V2 minus V1. That means 100.312 minus 100, that gives you 0.3. Right answer. Point question. Comparative questions, don't miss them. Yeah, what is this? Yeah, up to now we have done PMMC ammeter, right? Now we are going for PMMC voltmeter. A moving coil instrument having a resistance of 10 ohms gives full scale deflection when the current is 10 milliamperes. What should be the value of series resistance so that it can be used as a voltmeter for measuring a potential difference of 100 volts? See my dear, first of all, this is the diagram. So it is having a current IM and there is the internal resistance of RM. A moving coil instrument having a resistance of 10 ohms gives a full scale deflection when the current is 10 milliamperes. Current is 10 milliamperes. What should be the value of series resistance to be added? The question here is, what is the value of series resistor? What is the value of series resistor to be added so that it can be used for a measurement of how much? For a measurement of total voltage of 100 volts. Right? So, as you know, the formula for RSC, what is the formula for RSC? RSC formula, series resistor is equal to Rm into M minus 1. Rm into M minus 1. Rm we know, what is M? That is Rm into V by Vm minus 1. So first of all, you can calculate the Vm, right? What is the Vm? Vm is equal to Im into Rm. So that will be what? 10 into 10, 100 millivolts. Okay, so let me substitute here. The RSC is equal to Rm into M minus 1. Question Rm. What is Rm? 10 ohms. So this is 10. Sorry. So V by M minus 1. So here let me complete Rm 10 ohms V 100 volts, PM, that is a voltage drop across this, IM into RM, that is 10 into 10, 100 millivolts, that is 100 into 10 power minus 3. Simplify it, how much you are going to get? 100 gets cancelled, 1000 minus 1, 999. So I am going to get 9990 ohm. Option D is the, because up to now we have solved the questions related to what? PMMC ammeter. So this question is purely related to PMMC voltmeter. Okay, so 9990 ohms. Okay, dear, these are the questions, a full set of range of questions we have discussed in this lecture. Okay, so PMMC range of questions we have discussed now. Of course, applications of PMMC rectifying instrument, that will in the coming lectures will. So in brief, PMMC torque expressions, deflection torque bina, controlling torque Kc theta, that expression, shunt resistance ka formula, series resistance ka formula, that formula, add the waveforms, when waveforms are given, how to solve, that also, and comparatively with other instruments. Okay. I hope in this lecture you got the clarity about the PMMC. In the coming lecture, we will continue with our other instruments. Thank you, dear. We'll meet in the next lecture.